Hello friends, today we are going to start with a new topic called Maxwell Distribution. In Maxwell Distribution, what you have over here is like we have to consider a container containing gas, and that gas is in equilibrium, and the particles in the gas are having a velocity v, and that velocity v is being split up into three components. One is Vx, another is Vy, another is Vz. So the first consideration that comes from James Clerk Maxwell, is that the probability of finding a particle with velocity Vx in the velocity range Vx to Vx plus dvx is equals to phi vx dvx. This is the first consideration by James Clerk Maxwell. What is this phi vx? Phi vx is the distribution function. The distribution function, and this P is the probability of finding a molecule within the velocity range Vx to Vx plus dvx, and this dvx is the elementary cube considered in this dimension in Vx, Vy, Vz frame, having this is dvx, this is dvy, and this is dvz. So your velocity component in this direction is considered within this elementary box with sides dvx, dvy, dvz, and the probability of finding the particle within this Vx. So obviously we are talking about the velocity component in x direction. So it will be phi Vx dvx, where phi Vx is the distribution function, and dvx is the velocity component, is the elementary velocity component along the x direction. So similarly, if we wanted for all the three dimensions, then what would happen? Pvx, Pvy, Pvz is equals to phi Vx, phi Vy, phi dvx, dvy, dvz, where Fv is equals to nothing but phi Vx, phi Vy, and phi. This is our consideration that will be taken into account. Now we move to the determination what is this fv? You want to determine what is this function fv. So you take log on both sides. Log fv is equals to log vx plus log vy plus this is what you have. Now since each of these are independent of one another, so we can assume that ln fv equals ln vx. So differentiating this particular equation, what we add is f prime by fv with del v del vx is equals to phi prime by vx. So what we did, we are differentiating this particular equation with, now differentiating, it should be like this. With respect to del x del vx on both sides, so we can obtain this. Now what is this part? Now what is del v by del vx? So v is given as root over vx square plus vy square plus vz square. So this will be equals to 1 by 2 root v to v to vx. So 2 to cancel. So what we obtain is vx by root v. So this is what we have over here. So substituting over here, f prime v by fv vx phi prime vx. This is what you have. Now since this part is independent of Vx and this part is independent of any other Vy, Vz or any other term, so this part may be considered as 1 by Vx phi prime x by phi x is equals to some constant negative alpha. So we have phi prime x by phi x is equals to minus alpha x. So on integration we get an phi x is equals to minus alpha x square by 2 plus ln some constant a. So what do you have over here now? So phi x is equals to a exponent minus alpha x square where a alpha are undetermined constants. Now we would like to determine the constant a. Since we know a integration minus infinity to plus infinity exponential minus alpha vx square by 2 is equals to 1. Since this is a exponential function and obviously this is a distribution function, if we plot this distribution function will actually behave as a normal distribution. So the total probability distribution of this particular integration would give us 1. So we have to do this particular integration. This is called normalization of the distribution function. Normalization of the distribution function. From the normalization of distribution function, we know that this is equals to 1. So this is a standard integral, and the result of the standard integral can be obtained as root over 2 alpha root over 2 pi by alpha equals to 1. So hence a is equals to root over alpha by 2 pi. So our generally this phi equation now reduces to, I will replace this a by root over alpha by 2 pi. Now we have to determine another constant which is called alpha. since we know Vx square is equals to minus infinity to plus infinity Vx square Vx dx. So this is called, this expression is called squared mean. Squared mean velocity. What is squared mean velocity over here? So is equals to minus infinity to plus infinity Vx square. What is phi over here? Is equals to root over alpha by 2 pi Vxp minus alpha Vx square by 2. So this results to root over alpha by 2 pi. This is again a standard integral, and this can be written as root over 2 pi by alpha cube. So that is equals to 1 by. So what do you have? Vx square is equals to 1 by alpha. So what is this Vx square over here? Vx square over here is actually obtained from the pressure equation that we have already developed earlier. So let us check the pressure equation as we have seen earlier. The pressure equation was P is equals to 1/3 mn c square. This c square, we can write it like this. More simplicity, you can write Vx square plus Vy square plus Vz square. So assume that Vx is equals to Vy is equals to Vz. Then it becomes P is equals to mn V square, that is V say. If we assume that all the component velocity along this direction is same, Vx is equals to Vy is equals to Vz, suppose, then from pressure equation, another pressure equation from the equation of the scale, we have P is equals to N K T. So N K T, where K is the Boltzmann constant and N Mn that is what we had. So both sides get cancelled, and you have Kt is equals to mv square. So v square, if we consider it as a square mean velocity, then this velocity is same to this according to physical significance. You can write if this Vx, Vy, Vz can be same, can be equal to a velocity which is called square mean velocity. This is the physical significance of this V. So V square in this curly brackets you can write is equals to Kt by K. So you can substitute in place of 1 by alpha equals to kt by a, or alpha is equals to m by a. So we can safely put in place of alpha m by kt. So our phi equation in x direction, phi vx rather, would be in place of alpha we will put m by 2 kt, and here alpha is equals to m by kt, or you can write m by 2 kt. So this is your fundamental equation. Now the distribution function for the x direction has reduced to this function. So now we can write the capital function as that we discussed earlier, like it was like this. If v was this, if v is equals to phi vx, phi vy, and phi vz. So we can put these values over here, and we can write root over m by 2 pi kt whole to the power 3 by 2 exp. We can take common m by minus m by 2 kt. Then we have vx square plus vy square plus vz square. This is what you have. So what is this vx square plus vy plus square plus vz square? This is again the component of the velocity in single direction, m by 2 pi kt whole to the power 3 by 2 exp minus m by 2 kt, and this becomes v square. So this is your fv. Now if we want to find the number of particles within the velocity range v and v plus dv, then suppose this is b radius and this is dv. Now we consider this surface. So we want to find the number of particles within the velocity range v and v plus dv. So this is our shell under consideration. So the probability PV can be obtained as Fv into 4 pi v square dv for the number of particles into this shell, where Fv is the distribution function. So we can write PV is equals to, we already obtained FV over here, so you can put it safely in this place. We can write m by 2 pi kt whole to the power 3 by 2 into minus m by 2 kt v square into 4 pi v square d. So this is the probability of finding the particle with the velocity range v and v plus dv, for the Maxwell distribution of this particular ideal gas under consideration. Remember, we have done this Maxwell distribution for ideal gases only. There is no non-ideal gases into consideration. The ideal gases are only taken into consideration. So this is the amount of, or the probability, this is the amount of probability that we can get for the number of particles with the velocity range v and v plus dv. So this is your expression. That's all. Thank you.